right, good morning, ladies and gentlemen. Could you see me through there?
Yes.
Okay, so do this now. A capacitor has a distance of 0.005 meters between the two plates.
Between the plates.
And has an electric field of 25 Newton coulombs. What is the delta V, the change in the electrical potential difference?
That's right.
What equation are we going to use?
Well, they got to do that. They're on their own first.
Oh, okay.
Because you've got your notes there, right, kids?
What equation are we going to use? Number 2, what is the force on a +2 coulomb charge? And lastly, how much work to move that +2 coulomb charge from the negative to the positive?
That's right.
Yeah, take a second to do this.
Go ahead. And we're back.
Okay, let's go. Okay, so let's see. What is the electrical potential difference? What was that equation? Ed. Okay. All right. So let's go. I'm gonna go ahead and write down the numbers we're given over here. So we've got 0.005 meters, and my electric field is 25 Newton coulombs.
Yep.
There is a hair. Okay. All right. This is easy. I'm just gonna plug them in. Right?
Yep.
Newton coulombs times 0.005 meters. And we're gonna get, thank you. I had my mom brought my stuff yesterday. I was like, let me see if she's up. And if she's not working. Okay, I got 0.125. 0.125. What are my units here?
Newtons per coulomb per meter. Newton meters per coulomb, and Newton meters a joule, and a joule per coulomb is a
volt.
That's right.
Nice, Boykin. Okay, so what is the force on a +2 coulomb charge? Okay, so now my charge is +2 coulombs. Okay, we want to know the force. Okay, well we have the, what was my equation? Delta V is force over charge, right?
No, it's work over charge.
Electric field, right?
Yeah.
Even this more makes mistakes. I was trying to think about the units, right?
I make mistakes. I got out of bed this morning.
Yeah, so an electric field is a Newton per coulomb, force over charge. Okay, so here we go. We're trying to find the force, right?
Yeah.
I did that last time too. I was like,
I think that's going to be earthquake.
Earthquake. It is. So the Q goes over there. Okay, so the force equals earthquake. So here we go. 25 Newton coulombs times my charge, which is 2 coulombs.
I don't think you're going to need a calculator for this one.
50, and coulombs cancel. We're talking about force.
50 newtons.
50 newtons. Okay. You guys getting this so far? Okay. All right, number 3.
How much work to move that 2 coulomb charge from the negative to the positive side?
Okay. So
Work is
force times displacement.
Yep.
Okay, so we're trying to move that 2 coulomb charge up there. Do we have our force?
We just got it. It's 50 newtons.
Okay, so 50 newtons. Do we know how far it went?
It's up there.
0.005 meters. 50 times
2.5?
0.005. 0.25.
0.25. All right.
0.2. I'm like, it's only with a 2 and a 5. 0.25. We're talking about work.
And that's a Newton meter, which is a joule.
Mm-hmm.
Simple, yes?
Very simple. Okay, so what does each symbol represent? Okay, so we're talking about distance, electrical field, our test charge, force work, and electrical potential difference.
Or electric potential. Or potential difference.
Or the change in the electric potential. Or
That's a lot of syllables to say. That's right.
Okay, and then what are the units? Volts,
Yeah.
joules,
Yeah.
newtons,
Uh-huh.
coulomb, Newton coulomb.
Newtons per coulomb.
Per coulomb, sorry. Oh, yeah, sorry, per coulomb. Put a little division in there. And then meters.
Yep. Or centimeters or millimeters or miles or
If you want to get fancy with it.
yeah.
Okay. What does a voltmeter measure?
Our friend the voltmeter.
Okay, so our voltmeter measures the electrical potential difference.
That's right. Measures the difference in electrical potential energy.
Yes. It measures the difference in the potential energy from one side of the capacitor to the other. So whatever that difference is.
Yep.
Electrical potential energy, it reminds me a lot of gravitational potential energy.
There are many similarities.
Okay. So let's go ahead. I think this is the one. Oh no, I've got one more thing to do. Okay, how was work done in the capacitor lab? Yeah, let's bring it over.
Come here, you.
Come here. Okay, how was work done in the capacitor lab? So we'll pretend like these are all connected. Work was done when I cranked the handle.
That's right, because work is force times displacement in the direction of the force. That handle's not going to turn by itself if it's just sitting there. You had to do work turning that handle.
Okay, sweet. Now I'm going to go ahead and wipe my board off here as I prepare to answer these questions.
What did that work do?
And you know what? I'm just going to go ahead and link these in here as well, just so we can have the visual. Okay, so where's my black marker? Oh, here it is. Okay.
Yeah, you got your parallel plate capacitor that has got the electron pump hooked up to it.
Yeah, so what did that work do? I'm gonna go, and I'm gonna use pink and gray. I'm gonna do blue, because I don't have gray.
And that's the symbol for the electron pump. Rather than drawing this whole thing,
Yeah.
we're just going to symbolize, this is the two plates, and that's the electron pump.
Squiggly. And then the pink and the silver is the pink and the blue right here, the wires.
That's the conductors that allow electrons to move freely.
So we put work in, right? By by cranking that handle.
Yep.
Okay. And what did that work do?
Well, what does a pump do?
Well, a pump do.
What do pump do?
A pump moves something from one place to another place.
That's right.
Right? And so what we're moving here is an electron. We're moving electrons from here down to here.
If you take one electron away from the top plate, what happens to it?
Well, one goes here, and then this one becomes positive. I'm going to make these colorful. I know. Okay, if we pump an electron down here, this now becomes positive.
Yeah.
Okay, what if we pump another one?
Well, it makes it a little more positive on top, a little more negative on the bottom.
Pump plus, pump plus, pump plus. Okay.
That's right.
All right, so what did that work do? Essentially what we're seeing is we're moving electrons from one side to the other, which is increasing. And as we're doing this,
what happens to the work that you're doing?
Well, the work that we're doing is going to be stored in our electric field. Yes.
Yeah. Yep.
All right.
And
Our uniform electric field.
How can we tell?
How can we tell? Okay, so
Well.
oh yeah, when we look at our voltmeter, so as we crank this thing, right, it's not plugged up in, but as we were cranking this thing, okay, we saw that our voltmeter went up.
Yeah.
Right? Should we go ahead and do it?
That can't hurt. I'll let you do it.
The one-handed magician. Okay, pink, silver to black. So yeah.
Yeah, the voltmeter is measuring electrical potential difference.
So how can we tell that electrons are being pumped from one side to another? We look at our voltmeter.
Yep.
Right? Okay. Why did the handle keep turning when I let go?
That's a good question. It just happened. The handle keeps turning, but it doesn't turn forever. The voltmeter goes from that maximum down to 0.
Okay.
What's going on?
All right, so where's my markers over here? All right, so as we crank that handle, we're pumping electrons from this side to that side. This side becomes positive, this side becomes negative.
Yeah, and you have to do work because those electrons don't want to go.
They don't want to be over here. Now, what happens when I have a ton of negatives on the same side here?
Repulsion.
Repulsion, right? And so as soon as I stop putting work into that crank, we have this conductor here, this wire here, and what's going to happen is these electrons don't want to be next to each other. They're going to be like, ew, get me out of here. And so they escape back running this way. Okay? And what does that do to our handle here?
Well, it makes it start turning, yeah. The electrons do work on the electron pump.
But it doesn't just stop here, right? The wire connects to this side, so my electrons actually end up coming back this way.
It goes through it.
It goes back to the wire this way.
Yep.
So yeah.
It's simple.
Okay, I think I covered everything there. Oh, and I forgot to mention, what's another reason they want to come back over here?
Attraction to the naked protons!
The force of attraction. Yes, yes, yes. Okay. All right, so we turned the handle and took one electron pump clip off the capacitor. Want to help me with this one? Oh.
Stop turning.
Okay.
But we still have, hold on. We still have volts in the voltmeter. So what's going on now?
What was going on inside the capacitor and how could we tell? Okay. So first of all, as we pump our crank, I'm just gonna switch my arrows here. Okay. As I put work in, pumping my crank, electrons are turning my pump. Can't speak. Okay. Electrons are pumped from one side of the one plate to the other plate.
So you got all these electrons on one side, you're missing electrons from the other, and all of a sudden you disconnect one.
Burp, like this. So now where are the electrons stuck?
They're stuck.
Okay, and what does our voltmeter read when they're stuck over here?
Well, it shows that a work that you did is stored as electrical potential energy inside the capacitor.
So they're all stored over here. Okay.
Yeah, there's a situation that wants to go backwards. The electrons want to go back to the protons. They want to get away from each other.
Okay. So now when we reconnect this wire, what's going to happen to those electrons again?
Well, let's find out. It's alive! It's alive!
Yeah, so the electrons go back.
It's
this
dead!
way. Bada boom. Work is again seen through the handle of the pump moving.
Yeah.
And electrons go back to this side.
Yeah, and the field disappears on the inside. You got just two plates that are sitting there.
Yeah, they're just hanging. That's a really good point. We haven't mentioned that. So it neutralizes, right?
Yep.
Things are all happy now. Okay. All right, so we haven't gone over the homework for the lab yet. So
we did the lab. You had a bunch of questions you were supposed to work on. You could do it in class. You could do it at home.
Yeah. So last night you had homework for a lab, and what I'm gonna do is I gave you guys about 15 minutes to watch this video, and so that timer is gonna be up any time now, any second now. Maybe you got like 5 minutes left. With the rest of that 5 minutes before we go over the homework, go ahead and go to page 493, and you're gonna do number 6 and 8. Number 6 right here and number 8 right there while you wait for Miss Moore to be ready.
It's simple.
All right.